Need your pencil and your calculator on this quiz. Thank you. All right. Number 1 on page 22, part A is 0. Part B is the crate's at rest, so it's not accelerating. Number 2, part A is equal to. Part B is 0. Number 3A is equal to. B is 0. C is equal to. Number 4A is greater than. B is right. Number 5 is 150 newtons. 6 is 200 newtons. And 7 is 250 newtons. Any questions on that page? All right, then let's check the next page. I'll just give you final answers, okay? And if you want me to do any of them for you, I will. Number 1, the final answer is 211 newtons. Number 2, the final answer is 0.799. And number 3, the final answer is 51.9 kilograms. Any questions? Sure, number 3. All right, so in question number 3, it says that we have a rightward force of 405 newtons. So let me start with a free body diagram. There is this rightward force, which is 405 newtons, being used to drag a large box across the floor at a constant velocity. So since there's a constant velocity, we know there is a force of friction opposing this applied force and balancing it. So this is also 405 newtons. Now the box has some weight and there is a normal force acting up. These are going to balance as well. Now, it says that the coefficient of kinetic friction between the block and the floor is 0.795. So I know the mu k is 0.795. I want you to find the mass of this box. You can't do it in one step. You're looking for M, the mass of the box. What's up? Not quite yet. Let's take your quiz and then you can go. Okay, so to do this, gentlemen, I'm trying to teach, which means you should not be talking. So what I'm going to do first, knowing the force of friction and the coefficient of kinetic friction, is I'm going to determine what the normal force is first. And I'm going to do that using FF is mu Fn. So the Fn would be FF divided by mu. That is 405 newtons divided by 0.795. So when you go to your calculator and you round your answer to 3 sig figs, we find out that that answer is, I'm not sure, let me work it out. 405 divided by 0.795, I get 509 newtons for the normal force. So this is 509 newtons, and therefore the weight is also 509 newtons because those are balancing. It's not accelerating up or down. Now that I know the weight, I can find mass by using G equals Fg divided by M, which means that M is Fg divided by G. That is 509 newtons divided by 9.81 meter per second squared. And when you work that out, you get 51.9 kilograms for that mass. And that's how that problem is done. Okay? Anything else? Vicki? Number 1. Okay. In question number 1, it says we have a 28.6 kilogram crate sliding across the floor. All right, so here is the crate, and I know the mass of that crate is 28.6 kilograms. Now it tells me that the coefficient of kinetic friction is 0.750. I want you to find the force of kinetic friction between the crate and the floor. So what's acting on the crate would be its weight its normal force. Does it say constant velocity? It does not, so I do not know if it is accelerating or not, but it doesn't matter. Let's say the crate is moving this way, so the force of kinetic friction would be acting to the left. I'm asking you to find that force of kinetic friction. The way I would do that is by using the equation mu Fn is equal to the frictional force. I know the mu value, but I don't know Fn. But I know that Fn has to balance Fg. So I can find Fg first using the mass. To get Fg, we use the equation G equals Fg over m. So Fg is mg. That is 28.6 kilograms times 9.81 meter per second squared. When I work that out, that gives me 281 newtons for the weight. So that is 281 newtons, and the normal force is also 281 newtons. Now I have everything I need to get that force of friction by taking 0.750 and multiplying by 281 newtons. And when I work that out with 3 sig figs, I will get 211 newtons for that force of friction. Okay? Anything else? Okay, you can use your homework. You definitely need your reference table and your calculator for today's quiz. Let's take that. Please make sure when you get your quiz, you put your name on the top of it. And when you are done, turn it upside down so nobody can see it. Put away your math, or I'm going to take that and rip it up. Put it away. This is not math class. It's physics class. Well, good luck. You do not have unlimited time. When your quiz is done, just turn it over so nobody can see your work. Shane's first, and then you can go after the quiz. Give you 1 more minute. During the break. All right, let's make sure your name is on top of the quiz and then pass it down this way. Once you passed it in, I'll need you to take out your notebook. And we're going to start section G of this unit today, which deals with Newton's second law. Pass them in. And take out your notebook, please. Keep out your packets, your reference tables, your pencils, and your calculators. And we're going to start Newton's second law. Okay, Newton's second law. What I'll ask you to do on the quiz on this, which will be Thursday this week, we spent 3 full class periods working on this, so that's why it's going to take us a little while. I'm going to ask you to define the term force. I'll ask you to differentiate again between forces which are balanced and those which are unbalanced. So far, everything here is review. I'll ask you to determine the net force acting on an object, which again is review. You should be able to do that on a free body diagram. You should be able to state and then explain Newton's second law. That's new. And then solve problems with Newton's second law. And then in order to solve these problems, you will most likely need to draw a free body diagram. So, of course, you'll have to be able to do that. So to quickly review what a force is, it's any kind of push or pull that an object experiences because of how that object is interacting with things around it. All forces are symbolized with a capital F, and then we add a subscript after that to tell us which type of force it is, like Fg for force of gravity. All forces in the metric system are measured in newtons, which is a derived unit equivalent to a kilogram times a meter per second squared, and they're vectors. We draw them with arrows going in certain directions to show us which way the force is being pushed or pulled. So here is Newton's second law, and it's very wordy. Newton's second law says that the acceleration of an object as produced by a net force is directly proportional to the magnitude of that net force. It's in the same direction as the net force, and it is inversely proportional to the mass of the object. It's a very mathematical law which tells us how an object will accelerate when the forces on the object are unbalanced. I got it, Shalom. All right, so if you're like me, when you read that, you go, what? Huh? What does that say? What does it mean? So we're going to break it down into small pieces. The first thing that you need to understand is that this law is talking about when the forces on an object are unbalanced. Newton's first law tells us what happens to the object when the forces are balanced. So this is the unbalanced force law. And it tells us that when the forces on an object are unbalanced, it accelerates. And that's probably as much as you did with it in middle school. That when objects have unbalanced forces, they accelerate. Now, at the high school level, since we're in a more sophisticated type of class, you have to do more with that. What does the acceleration depend on? According to Sir Isaac Newton, it depends on two things. It will depend on how much unbalanced force there is, the net force, and that is a direct relationship between the net force and the acceleration. And it also tells us that it will depend on the mass of the object's inertia. And that's an inverse relationship with the mass. So anytime we see these kinds of proportionalities, they lend themselves to making graphs, which show these relationships. So I'm going to scooch over to my document camera so that way we can add in these graphs into our notes so that way we can show those relationships. Can I do that? Okay. So the first graph that we're talking about shows us the relationship between the acceleration on an object and the net force that's acting on the object. According to Newton's second law, Newton says there is a direct relationship between the acceleration and the net force. So if I were to make a graph of the acceleration versus the net force, we would see a diagonal line with a positive slope. So what does this mean? In terms of a direct relationship, it means that if the net force is multiplied by a factor of 2, then the acceleration will also be multiplied by a factor of 2. That's what direct means. What you do to one variable, you do to the other. It means, therefore, if the net force is quartered, which means it's multiplied by a 4th, then the acceleration will also be multiplied by a 4th. That's what we mean by direct relationship. Whatever you do to one variable, you do to the other. Exactly the same. Okay. The other relationship that's described is the one between the acceleration and the mass of the object. And Newton's second law tells us that there is an inverse relationship, which means this graph looks like a hyperbola. Means it looks like a hyperbola. So what does this mean in terms of the factors? Well, let's say that the mass is multiplied by a factor of 2. then the acceleration would be inversely related to that multiplication factor. The inverse of 2 is a half. So that means the acceleration would be multiplied by a half, not by 2. It also means if the mass is multiplied by a quarter, then the acceleration would be multiplied by the inverse of a quarter, which is 4. That's right. It would be 4 times bigger. And that's what these graphs are telling us. Okay, this is what we mean by direct relationship. This is what we mean by an inverse relationship. All right, so again, what does Newton's second law tell us? It tells us that when forces are unbalanced, the object accelerates. And the acceleration is directly dependent on the net force and inversely dependent on the object's mass. So what does that mean? It means as the net force goes up, the acceleration increases, and as the mass goes up, the acceleration decreases. That's what we mean by direct and inverse, which I think we already have in our notes. All right, so let's now look at how this comes out as an equation, because proportionalities give us equations in physics. So Newton's second law, the equation for it is A equals F net divided by M. Now this equation is on page 6 of your reference table. So let's turn to page 6 and check it off. It's right here. A equals F net divided by M. This equation is called Newton's second law. Some of these equations have names. This one does. That is the name of that equation, Newton's second law. You should already have checked off the variable lowercase a on your reference table, which stands for the acceleration in meters per second squared. You should have already checked off the variable F net, which stands for the net force. And you should have already checked off the variable M, which represents the mass in kilograms. So we just went through that. The acceleration is A in meters per second squared. F net is the net force in newtons, and M is the mass in kilograms. So remember something here. The newton is that derived unit. And so if I were doing dimensional analysis with this equation, I would have newtons divided by kilograms. But a newton is a kilogram times a meter per second squared. So if I were to change the newton out to this, kilogram times meter per second squared divided by kilograms, then the kilograms would cancel out, leaving me with just the meter per second squared, which is what I would expect. Okay? All right, let's go to your packet and let's turn to page 24, please. I'm going to tackle all of question 1 for you so you can see how these problems are done. And then we'll start going around the room. Number 1 asks us what acceleration is going to result when a 12 Newton net force is applied to a 3.0 kilogram object. And then what acceleration will we get if I put it on a 6.0 kilogram object? So this question has 2 parts. I'm going to divide up my question and answer space into 2 sections. I'm going to start with my guess method. I can see that I'm given an F net value equal to 12 newtons and a mass value of 3.0 kilograms. The unknown is lowercase a for acceleration. I'll use Newton's second law to solve this. A equals F net divided by M. I'll then do my substitution with units. 12 newtons divided by 3.0 kilograms, which means when I solve this, that the acceleration is 4.0 meter per second squared. Now, the second half of this question, yes. The second half of this question, I'm going to not use Newton's second law as a guess method. Instead, I'm going to use the relationships given by Newton's second law. When I look at Newton's second law, I see that there is an inverse relationship between the mass and the acceleration. When the variables are set up in this way, where one variable is on the left side of the equals and the other is in the denominator on the right side, that is always going to give us an inverse relationship, which means that in this case, I'm seeing that the mass is being multiplied by a factor of 2. That means the acceleration would get multiplied by a factor of 1/2 because of that inverse relationship. So that means that the acceleration is the value I calculated multiplied by that factor of 1/2. It's half of the value I found. So what is my new acceleration? 2.0 meter per second squared with the sig figs. Okay? All right, let's go on to number 2. We have a net force of 16 newtons causing a mass to accelerate at a rate of 5.0 meter per second squared. I want you to determine the mass. Mohammed, could you get us started with a given, please?
The net force is 16.
So F net equals 16 newtons. Nate, another given? So A is 5.0 meter per second squared. Hudson, what's my unknown letter? Lowercase m. Lila, what equation should we start with from our reference table? That's right. Now, it is not solved for m, so you have to do the algebraic manipulation to get m by itself. Colin, do you know what that equation for m is going to look like? No, F net times A does not equal m. Let's go through it. If A is equal to F net divided by m, the first thing I have to do is get m out of the denominator. You can't solve for it directly. So that means m times A is F net. Now, if I want m by itself, I have to undo the multiplication, which means we will divide both sides by A. So the equation for m becomes F net divided by A. So that's the equation that we're going to have. M is F net divided by A. Let's do our substitution with units. 16 newtons divided by 5.0 meter per second squared. And Dan, when we solve that, what does that give us for the mass? 3.2 kilograms. Very good. Okay, number 3, we have an object that's accelerating at 2.0 meter per second squared. Now, the net force is going to be tripled, and the mass is going to be doubled. What's the new acceleration? All right, let's go through the relationships. So first thing I see is that the net force is being tripled. Bryce, what multiplication factor is that when you triple something? You're multiplying by 3. Okay. I want to know what that does to the acceleration. So if we think back to Newton's second law, which says that A equals F net divided by m, Josiah, what type of relationship exists between acceleration and net force? Acceleration and net force is direct. When I put one variable in the numerator and the other variables on the other side, this is always a direct relationship between the two. So that means the acceleration is going to be multiplied by what factor, Mariah? That's right, a factor of 3. Okay, now the second thing that's happening is the mass is being doubled. Jalila, what multiplication factor is that when you double something? So what are you multiplying by when you double something? 2. What does that mean? The acceleration is going to get multiplied by, Shane? A half. That's right, because this is the direct, and this is our inverse relationship, as we showed here, right? Mass and acceleration are inverse. Inverse. So here's what we do. We take the given acceleration. We're now going to have to triple it, and then you're going to have it. So Jackson, what does that mean the new acceleration is? 2 times 3 is? 2 times 3 is? Well, you could do that in your head. 2 times 3 is 6 times a half. So there's my new acceleration, 3.0 meter per second squared with the proper sig figs. All right, number 4. We have an object again accelerating at 2.0 meter per second squared. The net force will be tripled, and then the mass is going to be halved. What's the new acceleration? So, Eric, what am I going to multiply the net force by? F net is multiplied by, when I say it's tripled, what are you multiplying by? 3. And what is the mass being multiplied by, Josh? 1/2. Okay. When I multiply net force by 3, Logan, what does that multiply the acceleration by? 3, because that's a direct relation. Nikki, what is the acceleration going to be multiplied by when the mass is multiplied by a half? That's right, inverse of a half. So what we're going to do is combine these factors, take your original value, you're going to have to triple it, and then double it. 2 times 3 is? 6 times 2 is 12. So that gives us an acceleration of 12 meters per second squared. All right, number 5. 2 students are discussing their physics homework prior to class. They're discussing an object that's being acted upon by 2 individual forces, both in the vertical direction over here. Now, the free body diagram is shown at the right. The variables are incorrectly labeled. Let's fix them. That should be Fn, and that should be Fg. What do you notice about these 2 forces right now, Marnay? They are balanced. Okay, so this is balanced forces. Now, continuing our reading. During the discussion, analytical suggests to Noah formula that the object under discussion could be moving. In fact, Anna suggests if friction and air resistance can be ignored because of their negligible size, then the object could be moving in a horizontal direction. According to Anna, an object that experiences forces as described here, which are balanced, an object could be experiencing motion as shown in this ticker tape. Brody, what is this ticker tape showing us? Constant what? Okay, so this is showing a constant speed in a straight line or constant velocity. So Noah formula objects. He argues that the object could not have any horizontal motion if there are only vertical forces acting on it. Noah claims that an object must be at rest, like on a table or a floor. After all, says Noah, an object that has a balance of forces will be at rest. Who do you agree with? Well, first of all, balanced forces is described by which of Newton's laws? We've talked about 2 of them so far, first law and second law. Mia, do you remember which one is the balanced force law? That's right. This is Newton's first law. Jacob, does Newton's first law say that if your force is balanced, you have to be at rest? What does it say? It could be. That's exactly right. So who is correct here, Noah or Anna? Anna. So Anna is correct because Newton's first law states that when forces are balanced, the object does not accelerate, meaning it's either at rest or it has a constant velocity. One or the other. We don't know which. All we know is that it is not accelerating. Very good. Number 6. We have an applied force of 50 newtons being used to accelerate an object to the right across a frictional surface. The object encounters 10 newtons of friction. Hello. So here's what we're going to do. First thing I'm going to do is I am going to correct this free body diagram by adding the arrows to the center because they must always come out of the center of the box. I'm also going to fix the symbols on this picture. FN, FF, FG. The FAPP can stay. I want us to use this diagram to determine what the normal force is, what the net force is, what the mass is, and what the acceleration is. Okay? So the first thing I'd like us to find is the mass of this object. Any ideas how you can use the values on that picture to help you come up with the mass? Use your reference table. These are your givens. You've got an FF, an FG, an FAPP. You're looking for M first. Nikki? Excellent. G is FG divided by M. So that means M is FG divided by G. Let's go ahead and plug in. That means we're going to take 80 newtons and divide by 9.81 meter per second squared. Notice the 80 newtons only has one sig fig. So let's work that out. With one sig fig, Mohammed, what does that mean the mass is? 8 kg. I'm going to take that answer and put it on the line here. 8 kg. We will take the rest of this for tomorrow. On the other side of the break, all you will need is your Chromebook for the lab. We can use the assignment for the diagrams. What's that, Jacob? All righty, thank you. That's what I said, yep, and that's what it said up there. That's why you can put everything else away now except for your Chromebook. Once you're back from break, please clear your desk of everything except your Chromebook. And you can open up to Lab 15, which is posted in Google Classroom. All right, as I've asked now, I think this will now be the third time that I'm asking you to do this. Clear your desks of everything but your Chromebook and open up Google Classroom to Lab 15. This lab, if you don't finish it during this class period, is your assignment due tomorrow, due before class begins. Now, I am not going to do this lab with you. Rather, I want to show you how to use the lab simulation to help you do the lab and just go over what I expect you to do with the lab. So that way there's no confusion about what's expected. So that way you can get 10 out of 10 the first time you try this lab. All right. So when you open up the lab, this is what the Google Sheet will look like. Let's get this back up here, disconnected. Not connecting. Let's try that again. I can't connect. So everything away except for your Chromebook. So Bryce, put away your notebook. Dan, put away your reference table on that scrap paper. Colin, put away your calculator, your pen, and your pencil. Second to reboot. All right, I got to get the display to reboot. Open up to Lab 15, and when you open up Lab 15, you will see that there is a link to a simulation called Physics Aviary. We have not used Physics Aviary before, but this will be our first time. This is not the last time we're going to use it. What I like about Physics Aviary compared to PhET is that every single one of us is going to get different data. And every time you open and close this program, you get all new numbers, which means that as you're doing the lab, one tab in the lab must be completed in one sitting. If you don't finish it, then the next time you go to open up the lab, you're going to get all new stuff. You're going to have to redo it. Okay, so keep that in mind. We're going to want to try to get everything done in one sitting without opening and closing the application. If I can just get this program to get my cast to work. Keep saying no displays. No displays available. All right, let me try this.